We are in 6.6, last section in chapter 6. We're going to talk about the central limit theorem, which is a pretty big theorem in statistics. So we had talked about counts and proportions, and just yesterday we talked about finding it for means, right? For finding the average of stuff. Okay. So we had all this here, and what we worked with yesterday was if our population is normal, then we can say the sampling distribution is normal. Okay. What we're going to talk about today is what if the population is not normal? Okay. What if it's skewed? Okay, or some other thing. Okay, so we're going to look at a little video here and think about what happens with the video.
Okay, so we had talked about if our population is normal, our sampling distribution is also going to be approximately normal, right? Okay, so what about if our population is skewed in some way? Okay, so say it's skewed here. If I take a sample of 5, okay, there's our sample of 5, there's the mean. I do that 100,000 times. Notice we still have some skew to it, don't we? Okay. Notice what happens when I do 10. Okay. So there's, with population of 5, whoops, I have to hit the mean here. Okay, so here's a sample of 5, here's 10. Actually, let's just make it 16. Okay, 5 and then 16. So if I do 100,000 of them, okay, I know that the bigger sample creates a smaller distribution, right? Okay, but think about the variability, not the variability. So we know that more in our sample is going to have smaller variability. Think about the skewness of it, though. See how this is skewed? Because our population was skewed. This one's also a little bit skewed, isn't it? A little bit less skewed, though. Okay, so let's say I go as high as this go. This would go to 25. Okay, and if I do it 100,000 times, notice it becomes even less skewed. Okay. So the central limit theorem says that as the number in our sample gets larger and larger, no matter what our population looks like, our sampling distribution is going to get approximately normal. Okay, so let me create my own custom. Okay, so here's my graph that I made. Okay, so there's our population. Okay, if I take 5 versus 25. Okay. Notice if I take 5, still pretty skewed, right? Still pretty messy looking, okay? But as I get bigger, it's not as skewed, right? Okay, not as skewed. And you can see the skew here is just a little bit to the negative, okay? The skew is a lot more to the negative, okay? So once again, to repeat the central limit theorem, as I get more in my sample, the shape becomes more approximately normal, okay?
So here's the actual theorem. The central limit theorem says that when n is large, so the number in our sample is large, the sampling distribution of the sampling mean is approximately normal. Now, that's very vague, isn't it? Large. Okay, so some different textbooks have some different numbers for large. Our textbook, and what we're going to go with, says as long as our sample is above 30. Okay, so if our population is not normal, as long as the sample that we're taking is greater than or equal to 30, it doesn't matter what the population looks like. It can be skewed, it can be uniform, it can be whatever. As long as we have 30 in our sample, we can say it's approximately normal. Okay, we can say it's approximately normal, and then we can use the mean and the standard deviation to find probabilities using normal distribution on Desmos. So let's do some examples. Okay, so Mr. Ramirez's class did the penny for your thoughts activity. The beginning of this chapter, we didn't do it in class because we weren't in class, but anyway. The histogram shows the distribution of ages, the 2,341 pennies. Basically, we're looking at pennies and the ages of them, sort of thing, okay? So you can see most of the pennies were more recent. There were a few older pennies mixed in. Okay, but if I was going to take a sample of size 2 from this population, would my sampling distribution be approximately normal? No. Okay, it would still be skewed to the left because I don't have enough in my sample. Okay, what if I took a sample of size 50? If I took 50 and over and over and over again, I know my sampling distribution would be approximately normal because of the CLT. CLT says as long as we're above 30, would say it's approximately normal. Okay, so let's do another example. Suppose the number of text messages, how many text messages do you send in a day? Okay, sometimes we do that in class, so I ask people to get out their phone and look at how many text messages they sent the day before. Anyway, during a typical day, by the population of students in a large high school follows a right skew. So if you think about a right skew, it might look like this. Most people send with a few texts. There are a few people that send a lot of texts. Okay, so that's our population. And this population has a mean of 45 and a standard deviation of 35. How likely is it that random sample of 100 students will average at least 50 texts per day? Okay, so we have an average here of 45. We want at least 50 would be 50 or more. So if I take a bunch of, I take 100 students, find their average. 100 students, find their average. 100 students, find their average. 100 students, find their average, right? This sampling distribution, since I'm taking a sample of 100, okay, I know it's going to be 100 is greater than or equal to 30, check. So by CLT, I can say the shape's going to be approximately normal. Okay, so I know that this shape's going to be approximately normal. It's going to have a mean, same mean as the population at 45. And the standard deviation, just like the day before, is the standard deviation of the population divided by the square root of n. Okay, we're taking 100 in our sample. Square root of 100 is 10, 35 divided by 10 is 3.5. So we have that distribution there. So we want to know the probability of at least 50 texts. Okay, if I take 100 students, their average is going to be 50 or more. So I want to know 50 or more. Okay, I want to know that probability right there. So I go to Desmos just like I've been doing all these other days and find that, and I guess I'll get that here in a second. Okay, so we found that probability there from Desmos. Okay.
Okay, so we said it's approximately normal because of the CLT. Our mean number of texts was 45 with a standard deviation of 3.5 text messages. So there's our distribution. And we want to know 50 or more. What's the probability of 50 to infinity? 50 or more comes up to be 0.076566. Okay, so about 7%, almost 8% of students would, 8% of the time, if I take 100 students, that their average is going to be over 50 text messages.
Okay, so we found that probability there from Desmos. Okay, one last problem for us to look at. Your company has a contract to perform preventative maintenance on thousands of air conditioning units in a large city. Based on service records from the past year, the time that a technician requires to complete the work follows a strongly right-skewed distribution. Okay, so once again, if you think about the number of hours it takes, most of the time it doesn't take too long, but sometimes it does take a long time, so there's a right skew to this. That's my population. Okay, and the average, the mean, is 1 with a standard deviation of 1.5 hours. Okay, so as a promotion, your company will provide a service to a random sample of 70 air conditioning units free of charge. So we're taking a sample of 70. Okay. You plan to budget an average of 1.1 hours per unit. Will this be enough time? Okay, so first, the shape. Okay, so I know that my CLT, since it's above 30, we know it's going to be approximately normal. Okay, so our distribution here is approximately normal. We know that the center is going to be the same as the center up here of 1. And our standard deviation is going to be that 1.5 divided by the square root of 70. Okay, and 1.5 divided by the square root of 70 gives me 0.18, we'll say. So we have a standard deviation of 0.18. Okay, so answering the questions, what is the shape? We know it's CLT, approximately normal. Calculate the probability average maintenance will exceed 1.1 hours. So 1.1 will be right here, around here. We want to exceed that. The probability it's going to exceed 1.1 hours. So we'll go to Desmos and find that probability.
Okay, so once again, we got the normal distribution with our mean of 1 hour and a standard deviation of 0.18 hours. Okay, and what's the probability it's going to exceed 1.1 hours? So minimum of 1.1 and a maximum to infinity. So there's about a 29% chance that our 70 air conditioners is going to take more than an average of 1.1 hours per thing, per air conditioner.
Okay, so there's a 29% chance it's going to exceed 1.1 hours. So, based on your answer to the previous problem, did the company budget enough time? Well, they probably they could put more time in, because there's 1 out of 3 chance, almost, not quite, but 3 out of 10 chance that it's going to exceed. So they could budget more time in there to make sure they have enough time to get it all done.